Okay, this is the Unit 7 portfolio assignment. In this particular portfolio assignment, you are asked to use derivatives to analyze, so to speak, a function for things like maximum points, minimum points, local maximum, local minima, global and vice versa, inflection points. So we're going to use first derivatives and second derivatives to do so. I have a function on the screen here, y equals 4x cubed minus 20x squared plus 8x plus 10. There's actually quite a bit you can tell about this function even without calculus. So for example, you may notice that it's a cubic function. That is a function whose highest degree, a polynomial function whose highest degree is 3. Okay, and we know that constant functions graph as horizontal lines. Linear functions graph as lines with a given slope. Quadratic functions graph as parabolas. And cubic functions have two turns. So basically, we can say that so for a cubic function, there are two possible turns to the function. Moreover, I can tell you that because the first term is positive, that this starts down on the left and ends up going up on the right. Now, what I don't know is if it does this or if it does that, right? Or if it goes way up and way down. There's lots of possibilities for this function. Okay, so we can tell quite a bit already, actually, just by the fact that it's a cubic function with a positive leading coefficient. But let's use our calculus here. Okay, I might be interested without calculus in finding the zeros or the intercepts of the function. I could try setting this thing equal to 0 and solving. That may or may not be very easy. In pre-calculus, you learned some techniques for trying to find using something called the rational roots theorem, if there are any rational roots. Most polynomial functions have no rational roots. That is, the roots that exist are irrational decimals that go on forever. So solving them is rather tricky. So we're probably not going to find any zeros that way. However, we can analyze the first derivative here. So remember what the first derivative tells me. The first derivative tells me the slope of the function at any given time, any given x value. So let's take the derivative. 4 times 3 is 12. X to the second, decrease the exponent by 1. 20, x to the second, 20 times 2 is 40x. And then 8. And then the constant function disappears when we take the derivative. Okay. At this point now, I'm interested in where the slope is 0, because these are my critical points. These are where the graph of the original function is going to be flat. So I'm going to set this equal to 0 and solve. Now you may notice that the coefficients all are multiples of 4. So I might try dividing everything by 4 to simplify things. And I get 3x squared minus 10x plus 2. Okay, 0 divided by 4 is 0. Okay, I might be tempted to try to factor this, but 3 times 2 is 6. There's no combination of factors of 3 and factors of 2 that when combined make a negative 10. So this isn't going to factor, so we're going to use the quadratic formula. For that, I'm going to use my Desmos calculator here. You can use your TI-84 or any calculator that you've got. Okay, I'm going to say A equals 3, B equals negative 10, and C equals 2. Okay, I love doing the quadratic formula this way. And then I just enter the formula. So negative b plus or minus, I'm going to start with minus, square root b squared minus 4ac all over 2a. Okay, and I'm going to call this R1. Okay, so my first root is 0.21. So x equals 0.21 is the approximate value that gives me a 0 slope. Okay, and then I'm going to do the same, copy, and I'm going to paste. I love being able to do this and change the minus to a plus. And change this to R2. Okay, 3.12 is the other root, 3.12. Okay, these are critical values, so they're points at which maxima and minima occur. I can actually tell you what these are already. I can tell you 0.21 is a max, and 3.12 is a min. And that's because I happen to know this is a positive cubic or positive third order polynomial. Okay, and I know it's going to behave like that. Okay, but let's use the calculus to take it another step further. Let's take the second derivative. Okay, all right, yeah, it's going to make me erase here. Let's use the second derivative. So y double prime. Remember, we're taking the second derivative of the original here, not the 3x squared. Okay, so 24x minus 40. Okay, one of the things I'd be interested in is finding out. Well, let's do the inflection points first. Okay, I'm going to do the not the inflection point, the critical values. So y double prime of 0.21. Okay, and let's bring up our calculator here again. Okay, so 24 times 0.21. In this case, I'm just going to use R1. I love being able to do that. 24 times the first root minus 40, and that way I get all the precision I need. So negative 34.87. Since this is negative, that means that the function at this point is concave down. And 0.21 is a maximum point. Okay? When you have concave down, curvature down, you've got a hill or a peak. Okay? All right, so the second derivative with the second root, 3.12 inserted. Okay? So let's try 24 R2 minus 40. And we get, yeah, look at that, the same value but positive. So R2, R1, okay. Yeah, make sure, interesting. Okay, so 34.87. And this tells me that this function is concave up, right? And that means that we're talking about a minimum point right here for 3.12. Okay, there remains one more thing to do, and that is let's take a look at the inflection point. So we're going to take the second derivative, 24x minus 40, and we're going to set it equal to 0. Okay, so 24x equals 40. X is 40 over 24. Divide by 4, 10 over 6. Divide by 2, 5 over 3. So we can say 1 2/3. Okay, 1 2/3. So when x is 1 2/3, we have an inflection point. That basically is the point at which we go from concave down to concave up. So now let's use this information. Let's use this information to sketch a graph or a picture of the point. Now we might want to get a few specific points of data here. So for example, I might want some function values at these specific points. So let's do this. Let's do y. Y of 0.21 and y of 3.12. Okay. And I want to find out the function values at those points. So let's do that here. So y is 4x cubed. So I'm going to plug in the roots. Root 1 cubed minus 20 root 1 squared plus 8 root 1 plus 10. Okay. And that's 10.83. 10.84. Okay, and y of 3.12. Okay, 4r2 cubed minus r2 cubed minus 20r2 squared plus 8r2 plus 10. Okay, so negative 38.2. Negative 38.2. 0.2, be consistent, 24. All right, so now I've got enough information, I think, to graph this. I might be interested actually in 1 2/3 as well. Y of 1 2/3 or 5/3. Okay. In which case, let's see. Let's say A equals 2 5/3. And then we do 4. Oh, I can't use A. I've already used A. That's why we're getting error messages. Okay, let's go R3. Okay, R3 equals 5/3. So 4R3 cubed minus 20R3 squared plus 8R3 plus 10. I get negative 13.70. Okay. So we've got some points here. So we've got 0.21, comma 10.84. We've got 3.12, comma negative 38.24. And we've got 5/3 or 1.6 forever, comma negative 13.70. Okay, so let's graph here. All right, I'm going to count by 1s going left and right, and by 10s going up and down. All right, so 0.21, okay, 0.21 and 10.84. That's right about here. Okay, and 3.12, 1, 2, 3.12, and negative 38.24, 10, 20, 38.24, right about here. And 1.6, so 1 2/3, and negative 13, so 10, 13. Here we go. There's that point. So I can now sketch, this is a maximum, this is a minimum, this is an inflection point. So my graph has got to do something like this. Right through there, it goes from concave down to concave up at that point, and like so. Okay, and that's a sketch of our graph. Now let's use Desmos to check. Okay, check a couple things here. So I'm going to go ahead and put in the function y equals 4x cubed. Y equals 4x cubed minus 20x squared plus 8x plus 10. Okay. Now my window is a little bit skewed here, so I'm going to set my y-axis to go from negative 40 to, let's go up to, our max was at 13, was it 13 or something like that? And let's go to 20. Okay, there we go. All right, and we can even scroll out and zoom out a little bit. Okay, and lo and behold, that matches our points. It gives our max 10.835. Okay, yeah, the 10.84. Our min as negative 38.243. Yep. Our inflection point doesn't come here, but let's do this. Let's do x equals 5/3, and there's our inflection point right there. Negative 13.704. Okay, so hopefully that answers your question. So for this portfolio, you of course are going to use your own function, do this kind of analysis, and then present it any way you like. I've made a video. If you can make a video, great. If you can make a PowerPoint, awesome. If you want to present it as in a Word document as kind of a written paper, that's fine too. It's up to you how you present your findings. All right, hopefully that answers any questions.